Study of interaction between shock absorber parameters influence on performance using continuous flow. Abstract. The oleo pneumatic CFD model was developed to study the interaction between various parameters to understand its influence on the performance of undercarriage shock absorber. The study on continuous fluid flow was focused on to understand the influence of orifice geometry and on other structural parameters including chamber geometry, fluid parameters, and influence due to interactions among them. The study was carried out using design of experiments, DO, for the responses. The results and outcomes are shown in the form of Pareto plots. Keywords: orifice plate, landing gear, undercarriage, CFD, design of experiments, oleo pneumatic. 1. Introduction. The major requirement of an aircraft undercarriage is to absorb the impact energy at the time of landing and also during taxiing, uneven surfaces, without causing any discomfort to passengers and crew. The rebound of the undercarriage after touchdown has to be gradual and not instantaneous. This behavior depends on the shock strut orifice, through which the fluid flows from one chamber to other. Investigations for the impact on undercarriage during aircraft touchdown using design parameters were carried out by many researchers using different approaches like statistical methods, analytical approach, and experimental techniques. 1. Undercarriage shock strut/absorber is major structural component which plays a very important role in determining the undercarriage performance and transfers landing load to aircraft structure. The slow extension of undercarriage happens due to the controlled flow of fluid from one chamber to other through an orifice, which directly relates to the performance of the undercarriage too. Researchers have studied the parameters influencing the undercarriage performance, which are rate of flow, orifice discharge coefficient, pressure drop across orifice, orifice dimensions, polytropic index, geometric parameters of chambers, length and diameter, air pressure 4, internal gas pressure, hydraulic fluid properties, strut stroke length, unsprung mass, vertical forces acting on the shock strut, sliding friction, static seal friction, etc. 1, 3, 4, 5, 6. Some of these parameters are investigated independently by researchers to understand the influence on an oleo pneumatic shock absorber in order to meet the undercarriage performance requirements. 4. From the literature it is found that no work was performed to understand the influence/impact due to combination of two or more input parameters and their responses, behavior, due to higher number of unknown parameters. Determination of displacement curve of an oleo pneumatic shock absorber is difficult due to the nonlinear motion of the shock absorber too. Institutions/industries developed their own methodology to determine the performance of undercarriages by assuming few parameters based on continuous flow, that have major impact, but the interactions between these parameters were ignored. Based on the certification agency's requirement, all the undercarriages are validated through testing, drop test, strength test, fatigue test, etc. Undercarriage testing is an expensive process and iterative in nature to arrive at the final design of shock absorber to ensure smooth and slow extension/rebound of landing gear for improved comfort of crew and passengers in the aircraft. In this paper, an attempt is made to present the interactions between the parameters during continuous fluid flow help us to understanding of undercarriage shock absorber design performance. The present work discusses the design of experiment, DO, method used for arriving at the optimum number of simulations required to assess the interactions between the input parameters, which are critical to the performance of shock strut, and at the same time maintaining the accuracy required for assessing the influences of different parameters like orifice geometry, orifice inlet angle, orifice outlet angle, orifice thickness, orifice diameter, chamber geometry, diameter of the lower chamber, and diameter of the upper chamber. Refer Figure 1 for the geometry details, gas pressures, mass flow rate of oil through orifice, etc. 3. A factorial design was chosen, since the numbers of parameters to be evaluated are large. The results and outcomes are presented in the form of Pareto charts, and the influence on the resultant due to the input parameters along with their interactions are discussed in detail. Figure 1 Flow model, concentric orifice. There are different parameters that needs to be investigated to predict the flow behavior, which can be taken forward for analyzing undercarriage behavior. For example, Reynolds number is important parameter for predicting the type of the flow, i.e. either laminar or turbulent. The study of orifice geometry, i.e. the convergent and divergent areas before and after, are important. The compression/damping load that is developed by forcing the oil through an orifice. Evaluation of the coefficient of discharge is helpful in predicting the pressure losses across the orifice. Studying the interaction between these parameters will give a better understanding of how to choose the appropriate parameter for further studies. Several studies exist in the literature for the equation of motion for the undercarriage, considering the UC as 2 degree of freedom system, so that the various performance parameters could be obtained from this equation. The equation of motion for the linear undercarriage was derived by Flugge 7 as. Also the pressure in the upper chamber was defined by Flugge 7. The values A0 and A1 indicates the area at different location on the piston, whereas indicates the pressure in both chambers when strut is fully extended and at rest. X, gamma and P1 explanation. The coefficient of discharge, which is a very important parameter for the characterization, was given by Benjamin 2 equals V2 H EQ4, where equals net orifice area equals dash equals volumetric rate of discharge. Multivariate optimization generally implies 2 steps: A. Evaluation using factorial design to identify signification factors, and B. An estimation of the response function. The parameters inlet angle, outlet angle, orifice thickness, in, orifice base thickness, in, orifice diameter, in, Q, mass flow rate, LB/S, and outlet pressure, psi, were studied for individual influences on the responses. 3. The possible interactions between the input parameters and each responses will provide additional interactions terms. In this paper, factorial design were used to determine the parameters along with the interactions that influences the responses: pressure at orifice inlet, velocity at orifice inlet, pressure at orifice outlet, velocity at orifice outlet, pressure at inlet, velocity at inlet, pressure at outlet, velocity at outlet, coefficient of discharge, CD. 2. General methodology. A simplified representative undercarriage shock strut continuous flow model, Figure 1, was developed with an orifice in the center to study the effect of parameters and their interactions during the constant flow of fluid from one chamber to other through an orifice. *CCM and was used throughout for the CFD analysis purpose. The CFD analysis model was developed based on past experiences using the following physics, like 3-dimensional space, steady flow, oil, segregated flow, constant density, turbulent and K-epsilon turbulence model. Refer Figure 1 for the geometry details. Each turbulent model has strength and weakness and is suited to a particular regime. The K-epsilon turbulence model is selected as it is robust, computationally cheap, offers good convergence and suitable for parametric studies, which is more relevant to the study discussed here. The fluid used in the analysis is schedule and its properties are given below. Density, 0.13 lb/in3. Viscosity, 0.02408 Pa/s. Mesh sizes were kept different for zones. Polyhedral mesh element with surface ream share along with prism layer to capture the boundary layer effects was selected. For surface mesh, the *CCM and has 2 models, i.e. surface ream share and the surface wrapper. The surface ream share improves the overall quality of the existing surface of the volume mesh models. The surface wrapper is typically used in concurrence with the surface ream share. However, as the surface wrapper make available the manifold mesh from a complex geometry, it is not used in the model described in this paper. The polyhedral mesh is selected as it is numerically more stable, less diffusive, and more accurate than an equivalent tetrahedral mesh. Moreover, also contains approximately 5 times fewer cells than that of a tetrahedral mesh for a given starting surface. The prism layer measures are generated next to the wall boundaries to improve the flow accuracy for the enhanced calculation of the several flow features such as pressure drop, etc. Figures 2 illustrate general structure similar to undercarriage flow structure. The element size is finalized after various iterations, sensitivity study, such that the flow field could be captured as accurate as possible. Also, 2 volumetric controls are created near the orifice to capture the detailed flow information. The boundaries are created at the inlet and outlet of the domain to specify the boundary conditions. A unique solution is defined by the boundary condition, and the properties which can be included in the boundaries are pressure, velocity, etc. In the present model, the mass flow rate is defined at the inlet and the pressure is defined as the outlet boundary condition. Some of the experiments were analyzed in MATLAB and the model is shown in Figure 2. The path in yellow highlights the liquid flow path. Figure 2, MATLAB fluid flow model. The MATLAB fluid model was carried out without convergent/divergent on orifice parameters and evaluated inlet pressure, outlet velocity. The available model in MATLAB was used and the minimum values in Table 1 was used for validation. Rec v. 2. Where is the critical mass flow rate? Is the dynamic viscosity? SR is the restriction area. Rec is the critical Reynolds number. SA is the nozzle inlet opening. PA is the nozzle inlet pressure. PB is the nozzle outlet pressure. Is the mass flow rate of the system. CD is the coefficient of discharge. U is the upstream density. R is the area ratio. 3. Design of experiment, DO, 3.1 DO model. A design of experiment is a statistical technique for analyzing experiments using series of tests. The factors are the input parameters that are varying independent variables, while the responses are the dependent variables which are measure of the outcome. Factors are the model parameters in which minimum and maximum values of a process or system are considered, so that we may observe the cause and effect relationship between the responses and factors in the process. The challenge was to define the DO methods with minimal number of analysis, to enable DO modeling with a feasible amount of effort. DO is chosen to reduce the number of analysis required by ensuring the uniformity and to capture all possible combinations of design points. A conventional and useful form of DO is the factorial design 2K. This is economical while also effectively covering the entire design space. Factorial design is the most widely used method for evaluating large number of factors in a limited set of experiments. Different fractional factorial designs can be created to estimate the interaction effects separately. There are 7 input parameters considered for this study against 9 output responses measuring influence of orifice geometry, chamber geometry, fluid pressure, and mass flow rate through the orifice as shown in Figure 3. 4.2 Coefficient of discharge, CD. The analysis were carried out using CFD software *CCM and the results were studied Pareto charts for various parameters like pressure and velocity at orifice inlet and outlet, pressure and velocity at inlet and outlet of the chamber. Display and processing of the simulation results are more relevant to this study are divided into various categories. The maximum value of average velocity is obtained near the orifice, i.e., where the flow is exiting the orifice, which is quite obvious phenomenon as the area is diverged near the orifice. Thus the separation of flow can be seen after the orifice exit area. The flow initiation starts from the inlet and proceeds towards the left of the model. The mass flow rate, which is directly related to the velocity of the flow, is one of the key parameters to evaluate the effect on different response parameters. Even the absolute total pressure varies from inlet to outlet. It can be seen that maximum value of the absolute total pressure starts decreasing once the flow crosses through the orifice. The major effect of any parameter, the minimum value to the maximum value, can be observed only near the orifice. That means the orifice area is very critical to the various response parameters. The interpretation of the factorial design DO were presented using the Pareto chart, from which the effect of individual parameter on the various individual responses can be predicted. The input parameters shown in Figure 3 are used to predict the consequence on the response parameters. The Pareto charts, Figures 5, from the DO results analyzing the effect on various input parameters along with the interaction on 2, 3 parameters using polynomial equation on the orifice inlet pressure on measured responses are represented in the Table 2 for various confidence levels. Based on the results obtained for pressure at orifice inlet, the response polynomial coefficients were determined in order to evaluate the statistical significance for each coefficient/responses using Pareto charts, figures 4. All coefficients with a t-value of 1.98 or above were considered significant. Table 2, Orifice inlet pressure. The above table shows that the orifice area and mass flow rate has a significant effect on the response, and also when they are combined, two factors, with inlet and outlet angle and thickness of the orifice has significant effect. The inlet and outlet angle of the orifice has moderate effect on the inlet pressure, whereas the interaction amongst them has higher influence on the orifice inlet pressure. As the number of interacting parameter increases from 2 to 3 and 4, the trend remains same except that the orifice thickness along with interactions with other input parameters shows good influence on the orifice inlet pressure. Orifice inlet velocity, orifice outlet pressure and orifice outlet velocity follows similar trends, influence of input parameters, and follows Bernoulli equation for steady frictionless incompressible flow along a streamline. EQ7. The figure 4 shows the influence due to interactions between more input parameters and their influences on orifice inlet pressure response. Figure 4, Pareto chart, multiple parameters interactions, for orifice inlet pressure. The non-significant response coefficients were deleted and the following significant polynomial response equations for pressure at orifice inlet were generated. There is a good correlation among the model's predicted SE and the experimental values R2 equals 0.8058. The table shows that the orifice area and mass flow rate and their combinations are combined, two or more factors, with inlet and outlet angle also have significant effect. The inlet and outlet angle of the orifice has moderate effect on the inlet pressure, whereas the interaction of them has higher influence on the orifice inlet pressure. As the number of interacting parameter increases from 2 to 3, figure 4, and the trend remains same for the velocity at orifice inlet, pressure at orifice outlet, velocity at orifice outlet, pressure at inlet, velocity at inlet, inlet pressure, and outlet pressure. The figure 5 shows the influence due to interactions between more input parameters and their influences on coefficient of discharge. Figure 5, Pareto chart, 3 parameters interactions, for coefficient of discharge, CD. The non-significant response coefficients were deleted and the following significant polynomial response equations for pressure at orifice inlet were generated. There is a good correlation among the model's predicted SE and the experimental values R2 equals 0.8629. The above Pareto chart, figure 5, shows that the inlet angle, outlet angle, and orifice area has significant effect on the response and has good influence with interacting among them, two-way as well as three-way interaction. 5 Summary/conclusions. Shock absorber CFD model was developed to identify the parameters which will influence the behavior of landing gear shock absorber using continuous flow and using design of experiments. Even though these analysis was for the continuous flow, but the number of parameters to be evaluated using constant volume in constrained flow and multi-phase problem required for shock absorber can be reduced. The analysis was carried out for 7 different input parameters, with traditional design of experiment to study the overall global trend and identification of key parameters based on the individual and interactions responses for further analysis in a contained volume, constrained flow and multi-phase problem. The parameters influencing the output variables were primarily found to be orifice diameter, mass flow rate, outlet angle and orifice base thickness are identified for further evaluation based on sensitivity analysis. As a result of the increasing complexity in CFD analysis, several responses should be simultaneously studied/optimized. Further work involving the study of the output vs key parameters may be taken up in the domain of interest using modern techniques such as Latin hypercubes and Gaussian surface response to ascertain the nonlinear behavior accurately.